DC motor speed control. From the diagram, we can see the proportional relationship between the speed of the DC motor and the applied voltage. Once the stiction has been overcome, the speed rises proportionally to the voltage. The speed of the DC motor can be controlled by simply controlling the input voltage. And this is the principle that has been exploited by the PWM. The PWM uses the proportional relationship between the voltage and speed to control the speed of the DC motor. The PWM allows user to adjust the average voltage going to the DC motor by turning the voltage on and off at a very fast rate. And the average rate voltage will depend on the duty cycle of the period. And the on and off period is one period is considered one duty cycle. The microcontroller generates variable pulse width through fixed frequencies, and the PWM is fed to the motor driver. To change the direction of the DC motor, we use a H bridge of the motor driver to invert the current flowing through the DC motor. So basically, the motor driver allows for speed control and change of direction. In the design of the MyteeMouse, the interrupts are created in the interrupt C, a separate file from the main program file. In the interrupt C, the instructions are coded in such a way that the timer 0 and timer 1 are triggered in the PIC18F microcontroller by using the tick from the rising edge and the falling edge of the quadrature encoder count to calculate the switch of the pulse width. The PIC18 microcontroller understands this operation and it expresses the tick from the timer and an external counter to the DC motor driver as PWM. The motor driver amplifies the current to feed the DC motor connected via the H bridge. This is how the interrupt works to switch the PWM. In the PWM interrupts, timer 0 and timer 1 are used. Here we see a flow chart about how each of those two timers would work to generate on and off times. And this is coded in as cyclic duty in the interrupt of the developed software. So here we see the timer interrupt service routine. Here is a block diagram of a proportional controller. The proportional controller maintains the offset error between the output of the system and the input. If there is no sudden change in the step input, the proportional controller is fine up to an extent because it will maintain the steady state error, which the system requires at this time to generate output. And basically, the difference between the desired position and the actual position is the error or offset, and the error is multiplied by the gain factor, and then we convert it to the positional error for the pulse width modulation. And this is then fed to the DC motor. These are the major hardware components that can be used to create a position controller for a DC motor. We have the microprocessor at the center, and then we have the peripheral connections. This is in the MyteeMouse robot, the HLC2705 optical encoder measures the position and pulses. It was employed as quadrature encoder, and it plays a very important role in the position control of the micro mouse. A round disc of 60 slots is mounted on the motor shaft, like you can see here on the gear encoder assembly. And then it is used to interrupt beam on the IR LED on the other side. So the interruption of the beam is used to generate pulse counting. One revolution of the wheel is calculated as 800 pulses. Here is a proportional control lab on the left motor. You can see that the desired position has been increased to 200 pulses every 2 seconds. And this is a quarter of turn of the wheel. The whole one revolution of the wheel is 800 pulses per rev. So the proportional controller needs the offset that is generating here to keep the system going. Software development. The software language for MyteeMouse was developed in C language for the saving of memory space in the integrated circuit. Hexadecimal code, binary operators, and unary operators were largely used in the coding. For simplicity, multiple files were used to develop the codes with such names as interrupt, init core, controller, global, LED PB, MyteeMouse, P18F4520, and the main program files. The multiple file approach simplifies the software and made it very intuitive. Some of the files were developed as header files and they were included as library or global variables elsewhere in the main program. This is a flowchart of the control logic of one of the controllers stored in the control.c. So here we see that when we push start, the system will initialize. It will decide whether you want to go forward or backwards, and then it will decide, it will establish contact with the other files and also with the encoder, and it will check position and pulses, and then it will check the current position, and then it will measure error. If you want it to go right, if you want it to go forward or backwards, it measures error, and it calculates the duty and the transfer function, and then it decides again you still want it to go forward or you want it to go backwards. If you want it to go forward, it sets the duty forward, it sets the direction for forward, and then it checks adds the bias to the duty that has been calculated, and then it starts and it checks have we reached maximum duty, and then it sets the PWM, and then it starts moving. And when the speed profiler sets in, that means you have a constant speed. So this is the offset. We're going to talk about the lab exercises now. So we can see that at the step input of 200, the KP at 5, it reached the peak overshoot. Then it bounced a few times. Then it settled at a steady state error. Steady state error is the offset. And when the P controller, with the P controller, if the step input is high, the KP is better when it's low, because therefore it will limit how much we can increase the gain. Therefore, it can become unstable easily. You can see on the other side, we increase the KP to 15, and due to the fact that the step input is 200, which is high, there is a constant oscillation, and it is not settling. The wheel has refused to reach a steady state, and the system has become unstable here. The speed profiler. The interrupt routine is not present here. A basic speed profiler has been used to implement the servo-controller for both the left and the right motor. And the speed profiler was made to generate a small step change every 10 milliseconds, and this resulted in a constant speed due to the fact that V is equals to N pulse over delta time. If we increase the amount of N every delta time, and there will be acceleration, but if we decrease the N, there will be deceleration. This is still the proportional controller, but here we have reduced the step input to 50 pulses, and we can see that the system is stable. It still bounces a few times before it settles down. Here we have the PD controller. This is a PD controller after it has been tuned and the derivative factor has been applied. The transient response time has decreased, and the overshoot has been drastically reduced as well. Well, because it attenuates the high frequency, and I was able to increase the gain by a lot since the step input has reduced to 50 pulses, and the KP is 25, and I also increased the KD too much. The only downside is that this may be overdamped. Here we can see the transient response. This is the result of my lab test. At dp equals to plus minus 50, the difference between P controller and PD controller is very obvious here. The transient response time has decreased in diagram B as opposed to diagram A. Conclusion is that the PD controller is a better option for the DC motor position control. And this is the end of my presentation. Thank you.